Niket enters one more time. All right. So the plan is first we're going to do basic measure theory in this course. So we'll do basic measure theory, and the idea is as follows: that in probability, as you know, there's an underlying sample space omega. We're looking for a probability measure on it, so that's a set function. So that the overall measure on the set omega, so this is a sample space set of all possible outcomes. So overall measure is equal to 1. It's normalized to that. Each set A gets a non-negative measure. And then we want this property, that probability of assigned to the union of sets AI, I from 1 to infinity, if they're disjoint. So if A1, A2, A3, so on, they're all disjoint sets, then probability assigned to this union should be some of the probabilities assigned to each of these sets. So that's the kind of probability measure we are looking for. And so this is a question now for TFR folks. How many of you are aware that this cannot be done in generality, that one needs to restrict oneself to a collection of subsets? And this is from a course that you've done in TFR or something that you learned from before? Yes, Saurabh, of course, would know from CAM course. But Malhar, do you know this?
Yeah, I know this. Sir.
And you know this from your own?
Yeah, from Vinod's course. Sir.
From Vinod's course. So this was covered in Vinod's course. So you actually did an example of a non-measurable.
We just said some basic example.
Okay. So maybe then we will construct a non-measurable set and have a small discussion of that. Agnev, do you know this?
Yes, but I have a question. Like, is this true for any measure P? Like, is there a measure for which this countable additivity is true for the entire power set? Like, except counting measure over some finite.
Yeah, I mean, I can imagine if you just kind of put probability mass on finitely many points, then you have no issue, right? So it can't be, it can be true for some nice probability measure in some nice spaces. So you need an infinite set, but even on infinite set, you can have nice infinite sets. But I think your question is that you've always seen this for Lebesgue measure. Is this true more generally? Yeah, but that's a fair question. We won't cover that topic. I can see how one would prove that more generally. Suppose you have a probability density on 0, 1, which is strictly positive. Then one can extend the argument from Lebesgue measure to show that even there you have an issue. Right? Even there you have subsets where you can't assign this. But yeah, so we are going to avoid that. Nobody else talks about it. So I'll have to construct an argument. I'll also ignore that. Okay. Okay, so that's what we'll do. So we will do some examples. So it may be repetition for some of you. But what would be nice that you may not have done is, we'll build this whole theory. I guess you probably have not proved Cauchy-Sequence extension theorem, right? At least not in Vinod's course, in the previous course in TFR. So we'll do that quickly. It's given in Royden, it's given a number of books, but nonetheless, we'll go through it quickly. The idea is that once you know that theorem, then we'll actually construct probabilities on Rn, Euclidean space in n dimension, R infinity, which countably infinite, product of R, and then uncountably infinite, R0t. So this is where you'll define something like Brownian motion, etc. And C0t, which is path of continuous functions. Just to show you these things, we won't spend terrible amount of time. I guess in some sense, you should get to see what is involved because it's cute and it's elegant. But the aim of the course is not to spend all of our time on these things. So you will get a flavor. And this is from Shreya. So we'll do that here. I mean, Shreya does a very good job of covering this stuff. So we'll go through that. I always thought that students enjoyed seeing this. So that's why we'll do this probability measure construction. Okay. And then, of course, all of you know that we have some, students here from outside of TFR who may be seeing this for the first time or maybe less familiar with it. So I'll go a little slow for them. So we'll define random variables, which are basically a function from the sample space to the real line, right? So every point in sample space is mapped to the real line. And then we want some additional properties from that random variable. Just the mapping is not enough. We want to say that if you look at the set omega, such that x of omega lies in an interval, right? Let me collect all the omegas in the underlying state space. such that x of omega lies in any interval, I should be able to assign measure to that set. So what I've said so far is, well, what I meant to say here was that we can't assign these three properties that I'm showing you right here. Let me just take a pencil. These three properties, let me take a different color. So in general, for all sets, you can't come up with a measure which satisfies these three properties. And we'll show that in Lebesgue measure setting. So it cannot be done. So then you say, okay, we have to be careful then. Things can go wrong. So we'll construct a subset, a collection of sets on which we can assign measure. So this will be a sigma algebra for those of you who know. And we'll talk about what sigma algebra is in the next class. It's a vast collection. It's very difficult to come up with sets which don't belong to this collection. Right? But nonetheless, then we'll discuss. Now we'll talk about such collection on, if the omega is Rn, then what is that collection? If it's R infinity, then what is that collection? So we'll do some good examples of such a collection on these spaces. R0t just means, think of it as continuous, as paths from time 0 to t. These need not be continuous. All possible paths, all possible curves, so to speak, they can be disjointed. And let me collect all of them. That's my sample space. So each outcome is actually a path, it's a function of time from 0 to t. Right? Not just continuous function, could be any arbitrary function. Let me collect every such thing. That's my space R0t. And the question is, how do I assign probability measure on this space? And similarly, C0 infinity, this means all continuous functions indexed by time from 0 to infinity. So all paths continuously going from 0 to infinity. Let me collect all of them. Let me construct a sample space with all these paths. Then let me collect a collection of subsets, which is a sigma algebra, which is a vast collection. And then I'll discuss how to assign probability measure to all those sets in an unambiguous manner. So there can be no contradiction. Everything is nice and clean and clear. So we are setting basically foundation on probability where there's no room for contradictions. Because as I mentioned, some of you are from other course, I guess. Yeah. No, it should be, this bracket is actually a square bracket. 0 to infinity. Not so important, one can do it on both, but okay, right. So we'll discuss all of these things, and there we'll get somewhat technical. So I'll just show you all the kind of intricacies that come into that. Often I make students prove some of these things, but this time maybe I'll just do it because I haven't done it in a long time. Okay, so now that we've done this, now we'll define these functions on this sample space. Now we have this underlying sigma algebra where we can assign probability measure. And the point is these kinds of sets. So X should have this property that omega such that X omega lies in an interval AB for any AB. We should be able to assign probability to that set. So that set should be measurable. So that's the kind of property we're going to impose. So that's the extra thing we impose in when we do things more rigorously. This is the same thing which people do with functions. If it's a function, if X was a function from a sample space to R, it should be a measurable function. So we'll talk about analogy of functions and random variables when we come to it. Okay, so this is going to be our this is what we're going to do in the first maybe 1 or 2 lectures, maybe 2 or 3 lectures, because we're going to prove some big theorems in it. I mean, to my mind, Cauchy-Sequence's theorem, for those of you who are kind of familiar with the statement, tells you how you define probability on some sets which are easy to define, algebras. Like on the intervals in 0 to 1, I know what the probability is going to be. I know how to do it. Then I get a unique extension to a much broader class. It's probably one of the most elegant theorems I've ever seen. I think most of you will also agree after going through it. So we'll go through the proof of that. It's just something kind of, it's beyond the individual imagination. Enormously smart people must have worked for a long time to get the theory right. So we get to see that. Okay, now that we've done this, now we want to define, we know what this means in elementary probability. It's a Rayman integral, right? F of x dx integral. You make a curve, f of x. You want to find the area below that curve. So what you do is you just chop AB into rectangles, right? This is your curve, f of x. You want to find this area between A and B. What you'll do is you'll just chop this into rectangles, right? Like this. So on and so forth, right? And then you sum up the area of the rectangles. We know what that is going to be. And now you chop them finer and finer and finer. Your area is increasing. What it converges to in the limit is the area below the curve f of x dx. That's how we define the integral. Okay. Now now that we are kind of considering, so I should say something about these functions f of x or random variables. These are measurable functions or random variables. They are much more general than the typical functions that you're used to. So typical function where, this Rayman integration, which I just showed you here, if I tell you that f of x is 1 on irrationals and zeros on rationals, you won't be able to find this integral for it. Right? Just as a first, as a simple function like this, you don't know what to do with. Now, when we do more general measurable functions, this is like the first function that you know what to do with. And you can construct much, much more general functions. So class of measurable functions is far more than just class of continuous functions. So we'll be working in that rich class of functions. So then the question is, okay, how do we integrate that rich class of functions? Right? So we come up with a very nice theory. This is from Lebesgue, again, a lot of activity from the early 20th century, which tells us how to construct integral of a function with respect to general measure on the underlying space. Now, all of this will become clear in the next few classes, when we talk about different measures on the underlying space. But in particular, where we're going with all this is, we'll be able to define integral of a function of a random variable with respect to probability measure. And this we call as the expectation of the random variable. So the expected value, which we think of as a very simple operation, all possible values that the random variable takes, weighed by the probability with which it takes those values, let's sum that up. That can be generalized substantially. So if you're seeing this stuff for the first time, it's a little daunting. So it, usually it takes a few times to see it, to really get a hold of it. But it's enormously beautiful and elegant theory. So you realize the power of kind of doing things in some kind of depth. Yeah, I mean, the problem with all of this is, and this I experience with students, is that, when you do too much math with them, they forget that probability also has an intuitive element to it. At the end, you need some intuition that you get from doing simple things to guess what things might look like in a more complicated setting, to make bold conjectures. And then you do your mathematical technical machinery and prove bold conjectures. So you should not lose sight of that. You should not get so overawed by mathematics that you forget that you also should have some intuition for these things. That's why probability should be done at the elementary level first. So you get to appreciate the intuition before you end up doing more complicated things. All right, so we'll define this Lebesgue integration. And then we'll talk about things like, convergence theorems, LP norms. So most of you know what these things are, right? LP norm of random variable x is just expected value of absolute value of x raised to power p for any p, let's say, greater than or equal to 1. And then you take the pth root of that. So that's a norm. It's a norm, meaning it's like a distance. It satisfies properties of a distance. So now you can collect, all the random variables for which this, this norm is finite. And that's a nice Banach space. For those of you know what Banach space is. But let's not get bogged down by that. We don't need it right now. And then we'll talk about, once we define this space, we'll talk about, okay, we should talk about it being a Banach space actually, because we will show that this space is complete. Now, Malhar, have you done this already in the previous course, that LP space is complete? Agnev, do you know? Okay.
Yeah, a bit.
In the last course. Okay. Yeah, the point is complete is, so Banach space means it's complete, that if you have a sequence in that space which is converging to something, then that point should also be in that space. Just to give you a very quick example, if I look at all points, this is 0, this is 1. This is what Saurav was kind of hinting at its earlier point. So if my space is, now is this a complete space or is it an incomplete space? Anyone?
Yeah, it's not.
Yeah, Saurav, I won't ask you to talk, so that's fine. He's had some stitches taken off. Anybody else wants to explain why it's incomplete? Speak up.
We can take a
you
Cauchy
take-
sequence converging to 0.
Yeah. You can basically take any sequence converging to 1 minus 1 by n equal to xn. Right now, this is converging to 1, but 1 is not in my space. So in this sense, my space has a hole in it. You have a sequence which is converging to a point which is not in that space. LP space doesn't have that hole. So if I give you a sequence of random variables, xn, and as Agnev said, so okay, it has to be a Cauchy sequence. So Cauchy sequence means that, okay, all the points are getting close to each other. These points are going to 0 for all n and m going to infinity. So these points are getting closer and close to each other. When this happens for real numbers, when the points get close and close to each other, they converge to a point in the real line. So the question is, in the LP space, does it converge to a random variable in the LP space? And the answer is yes. So we'll show that it's complete. And we'll talk about different modes of convergence. Some of you know point-wise convergence. If I give you just a bunch of numbers, what does it mean for them to converge to a limit? But in probability, we have very different ways in which random variables can converge. So xn converges to x almost surely with probability 1. So set of omegas where you see convergence, that has probability 1. Right. So suppose, so let me give you an example. Let me ask you a question here. So suppose my space is omega infinity, which is all omega such that omega is equal to, writing it badly, and each omega I is either heads or tails. You get the idea, right? Collection of coin tosses, infinite collection, heads and tails, right? And suppose probability is given such that heads has probability p, tails has probability 1 minus p. And now suppose xi omega is equal to 1 if omega I is equal to h is equal to 0 if omega I is equal to tails, right? And I want to say that x1 omega plus xn omega. So we'll discuss later that all these are nice random variables. We'll define a sigma algebra, but let's not worry about that right now. We want to say that this is converging to P, right? Almost surely. So what does that mean? Anyone?
So you collect all the omegas such that this thing like x1 up to xn omega divided by n that converges to p, and the probability of that omega will be 1.
Probability of this set will be 1, right? On each, we'll look at all these omegas. So once we fix an omega and outcome, a sequence of heads, tails, all of that. Once we fix that, then these are just a bunch of numbers, right? Some are 1, some are 0. It's a sequence of numbers. This sum is, this, let's call this as Sn omega upon n. So Sn upon n is also a sequence of numbers, right? So we'll fix an omega. Now this sequence of numbers could be either diverging, doesn't converge at all, or maybe it converges to some value. We look at all the points where it's converging to P. It's getting arbitrarily close to P eventually. We collect all such omegas. And then we say, okay, what is the probability of that set? Now, before we say what's the probability of that set, the set itself should be measurable. You should be able to assign probability to that set. So let me give you a representation just to save time. So convince yourself that this is the set that we are looking at. M equal to 1 to infinity. n equal to 1 to infinity, I guess. And then n greater than equal to n omega such that Sn omega by n, minus p is less than or equal to 1 by m. So you'll have to convince yourself that this is exactly the set where Sn by Sn omega is converging to p. In the sense that for all m, there exists some big n, such that for all small n bigger than that big n, Sn by n minus p is less than 1 by n. Right? So your earlier definition of convergence, in this, you have to show that both the sets are we're talking about the same set basically. Right? If omega belongs to this collection, then it belongs to your earlier definition of almost sure convergence and vice versa. But the thing is, this is now a countable union of sets on which we can assign probability. So it's a measurable set, exactly. Right? So we know how to, we can talk about probability of this set. Because before we say something happens almost surely, we should be able to talk about probability of that set. So yeah, so that's so that's what we'll see. When does xn converge to x almost surely? And then xn converges to x in probability. So we'll talk about what that means. Xn converges to x in the LP sense. Xn converges to x in distribution. All of these are different notions. Xn converges to x pointwise. All of these are different notions of convergence. So we'll see them a little carefully. And we relate them. We'll see examples where you have convergence. So almost sure convergence will imply convergence probability, but not the other way around. This, I presume, you're all familiar with Agnev Malhar. Is that right? Yeah. Okay, good. So we'll try to go through these things a little fast then, I guess. And then once we've done that, the question we're trying to answer is this. Suppose we have xn converging to x almost surely. When is it true that the integral xn dp converges to x dp? Integral of xn converges to integral of x. That is expected value of xn. See, this is just the expected value of xn. Integral with respect to probability measure. When is the expected value of xn converging to expected value of x? This is enormously important result. You show sequence of random variables are converging, and it's not always true that their expectations are also converging. Expectations are just real numbers right now. So are they converging or not? So we'll talk about these things. This also, I presume, Agnev Malhar, you've done this already. Is that right? I see. So monotone convergence theorem, dominant convergence theorem. Did you prove these theorems or did you assume them?
Like we haven't done the proofs in detail. Like we were taught Fatau's lemma and
Fatau's lemma and all that. Okay. But so it's okay if we do them. We do the proofs this time, right? So that's the extra thing that we do. I guess we prove these things. Okay. So we'll do that part. So this is all the kind of technical machinery that we're building up. Then we'll talk about, okay, if we have a function of two variables, x and y, when is fxy dx integral over y? The whole thing now it's a function of x integral over, fxy, yeah, it's function over y. Yeah, I don't know why I've written it in this manner. Let me just, okay, I can't correct it here. What am I trying to do? Let me just do it here. I guess this should be x and this space should be y. So, so I've written it opposite. So the point is, normally we know these things in the elementary integral theory that we can integrate first with respect to x, and then we get a function of y, and then we can integrate that with respect to y. And we can also do these things in the other order, first with y and then with x. The question is, when are the two equal? So that's called Fubini's theorem, and we'll do that in great generality, right? We'll do this we'll define what does it mean for a function of two variables. So there's a product measure underlying. So this integral will be well defined. And then we'll define these individual separate integrals, and then we'll integrate that. So all of these things we'll do more carefully. So when can you do all these things? But before we, do all the stuff, I guess many of you already know when this integral interchange can happen, right? So what's the answer?
So continuous partial derivatives.
What's that?
It's when the integrand has continuous partial derivatives.
No.
No.
We don't need that. I mean, what you need is non-negativity will suffice. It's like when you have discrete series.
Right.
So non-negative, that generalizes.
If you take discrete series like summation n equals to 1 to infinity m equals to 1 to infinity a and b n.
Yeah. Saurabh, you don't have to talk here.
Or something like if you take absolute value, then it should be convergent.
That's right.
Still be convergent. Yeah.
That's correct. Yeah. So if the absolute value of any of these integrals is finite, then you can do this. Because then you don't have to worry about infinity minus infinity settings. That's the concern in all these things. So we'll do this carefully. Maybe I'll do a little bit and I'll ask you to read up some of this stuff. So some of this stuff after a while is mechanical. So by the time we reach here, I'll just give you a flavor of what happens and then you can take it from there. Okay, and then we'll talk about conditional expectations and their properties. So how do you define E of X given by? So in elementary and again, I take it Agnev and Malhar, you're the two pictures I can see right now in my screen. That's why I'm going to refer to you right now. But you've seen this conditional expectations also defined with respect to sigma algebras. Is that right?
Like in Vinod's course, we have seen this defined for random variables, not sigma algebra.
Not sigma algebra. Okay, so good. So now we'll do these things in the sigma algebra setting. So again, very beautiful stuff. Kind of annoyingly non-intuitive. Like there are many things in probability or this kind of stuff that get with some people you just like them because you know them long enough. So some concepts you like them because you know them long enough. They don't come naturally. So it has that flavor to it. The conditional expectation. You kind of you think you know it because you have an intuition of what it should be, but it's not quite like that. So but then you become familiar with it, and then okay, it's fine. So this is one of those concepts. So we'll see that. I mean, you'll see what I mean when I get there. But this looks nice enough. E of X given y. It's like okay, it's just a random. Given y is taking some value small y. Our probabilities have changed now. We have new probabilities. So what's the conditional expectation of X with those new probabilities? So that's an elementary idea of E of X given y. And then you can see that the property of that is that will integrate just like X on the sets A, which are a function of y, which basically lie on y. So y lies between A and B. On those sets, this will integrate like XDP. What's nice is going to be in the general setting, this is going to be the defining property of E of X given y. That's how we'll define this random variable. It will be a random variable with this property. So you'll see it's a little kind of, it's to show things in generality. There's some non-intuitiveness involved in these things. And then so like obvious properties like E of X1 plus X2 given y should be equal to E of X1 given y plus E of X2 given y. You'll see it's not so straightforward to show. Even to show this, it takes a bit of effort because we're showing this in great generality. And there are a lot of other properties of conditional expectations. So we'll do all of that. And conditional expectations will not be defined with respect to random variables, but with respect to sigma algebras. And we'll see what sigma algebras are. So just, we're, generalizing all the things naturally to as far as we can. All right. So once we've done this, but from our point of view, let's just think of E of X of y exactly as you have in elementary probability. It has a very nice intuitive content. So if you take that view right now, then understanding martingales becomes easier. Now, you've done martingales as well in the previous courses, right, Malhar Agnev?
We did Markov chains.
Oh, you didn't do martingales this time?
No, but we didn't do martingales.
Oh, very good. That's good to know. So I'll focus more. Yeah, I mean, you can't get more elegant things in probability than martingales. You can do magic with martingales, basically. So martingales came about in the late 40s and 50s. And a lot of things which were done much, much more tediously with great difficulty can be done in great generality, much, much more simply using martingales. It's amazing what all can be done. And let me give you a flavor of that. So what's a martingale? So it's a sequence of random variables, collection of random variables, such that expected value of mn plus 1 given mn, and here I should really write given m1 through mn. So given the whole past history, what's the conditional expectation of mn plus 1? It's just equal to mn. So it's an idea of a fair game. On an average, I've remained the same. I had mn was my winning, let's say. This is all kind of inspired by gambling, like all good things. So probability is largely inspired by problems that arose in gambling early on. Exactly, sort of. So given x1 through m1 to mn, I'm going to observe mn plus 1. It's on average, it's going to stay equal to mn. It's not going to change. An example of that is, okay, think of mn as just sum of n independent variables, x1 through xn, which have zero mean, and they're independent. Independence is not so important, but yeah, I guess it is somewhat important. Let's assume it's independent for now. So given this mn, now you can see that the expected value of mn plus 1 given mn is just equal to mn plus expected value of xn plus 1 given mn. And xn plus 1 is independent of mn, and its mean 0. So that goes away. So it's a martingale. So this, this random walk, these are called random walks, which are sums of zero mean random variables. These are called kind of zero mean random walks. Are of course very common in probability. A lot of probabilities kind of studying of random walks. So these are martingales. And now, you can ask yourself, like going back to the gambling strategy, you've gone to a casino and you say, okay, I'm playing a fair game. You never play a fair game in a casino. Casino is always going to have a higher probability of winning, higher expectation of winning than you do. But suppose in a utopian world, there is a casino which offers you, a fair game, right? And now you pick up a time tau. You say, okay, I can't beat the system as things are, but I have my own rules. I've seen it in the past. Whenever I won 20 rupees, I stop. Or as my wife says, whenever in the stock market, I've got 10%, I just get out of the market. So you have some rule like this, right? So the question is, can you come up with a rule like this and make money from nothing? Can do better than just staying, because this tells you right away that E of mn plus 1 is equal to E of mn is equal to E of m1 is equal to m0, right? Does there any generalization for random walk in Rn2 like we do in R2? So your point is, can one talk about martingale in multiple dimensions? No, I don't. I think, you'll define maybe a vector of martingales. But I mean, you still think of them as kind of objects on the real line. So you don't prove theorems about a vector of martingales. At least I've not seen that being done in a fruitful manner. So I mean, it's a fair point that is there something to be gained by thinking of these objects in a more abstract setting? I don't think so right now. It's not, at least it's not gaining traction doing it that way, but it's a fair question to ask. So the question is, suppose, I'm going to stop at a random time. So, I guess most of you, at least from TFR, know what a stopping time is, but we'll define it here. So it's a random time for now. Let's just take it that way. So if you stop at a random time, for example, when my winning is 20 or when I've lost 40 rupees, or, I played 50 games or lost 40 rupees, some reasonable criteria like this. Some time where you're not allowed to look in the future and then decide to stop in the past, so that kind of cheating is not allowed. Then can you beat the system? So there's a, very kind of elegant Martingale stopping time theorem, which says that in large generality, you cannot. Expected value of m of tau, stopped random variable, is going to be equal to expected value of m of 1. So you can't beat the system. Now, there's always a strategy of beating a system. I've discussed this with, so we have some people here from Ashoka who are joining us in this class. I'm teaching I guess, basic probability course there. But I discussed one example with them of, even if the casino is unfair to you, you play a game where there's like 80% chance they will win, 20% chance you will win. How do you defeat it with probability 1? So does anybody from TFR want to tell me what would be a good strategy to defeat a casino in a?
Is it keep betting more and more until you win?
That's right. You double basically. I mean, doubling is one strategy. You bet 1 rupee, you lose. You bet 2 rupees, you lose. You bet 4 rupees, you lose. It's a geometric random variable, right? First success. So every geometric random variable is finite with probability 1. So eventually you will win, and then then your overall winning is positive. So that's one game where you always win. So this Martingale stopping time theorem has to exclude that possibility. So that's assumed away. So you build in conditions for this theorem to be true, so that those kind of strategies are at least ignored. Yeah, when you do with random variables, you always worry about things blowing up to infinity, etc., things becoming too large, etc. So you have to have some assumptions to take care of that. So that's a flavor, yeah. But nonetheless, you'll see this theorem, it's quite elegant. And what's nice about Martingales is that this condition that I'm showing you here, it's not a very demanding condition. It's easy to perturb random variables to get this to be satisfied. So it's easy to construct Martingales. And once you have Martingales, then you have all these theorems which are available to you. So that's the strength of Martingales. The most beautiful theorem is this one here. If you have a Martingale Mn, it actually will converge to some random variable M infinity almost surely. Now, we already kind of saw that almost sure convergence is not an easy thing to show. You can imagine that, right? Because we're asking for a lot. But if you have a Martingale, and if it's L1 bounded, that means if expected value of Mn sup maximum over all n, each E of Mn is going to be finite. But if this supremum is also finite, so your Martingale is not growing too much. This will not be true for random walks. And random walks don't converge almost surely like this. Then you do get convergence. So, it's just under this mild condition, you get almost sure convergence. So a lot of what we try to prove in probability theory, where we prove convergence to a random variable, relies on using the right kind of Martingale. Makes things much, much simpler. So in particular, the strong law of large numbers. Now you probably know what a strong law of large numbers is, right? Exactly what we did. Sn by n converges to its mean. We'll see with Martingales, you get a 2-line proof for it. I mean, you need a lot of machinery to get there, to get to those 2 lines. But once you get there, then you get simple proofs. So it's a great tool to have. And it's, it's also very kind of, it's not that technically demanding. All right. So we'll do all these things. And then we'll talk about, okay, L2 Martingales. As I said, this is bounded in this sense. So it's stronger than L-well boundedness. And then you get this convergence. And then you can also talk about things like expected value of random variable M given x1 through xn. It's like x1 through xn is the information we are gathering about something. M is a random variable that we don't know, and we're learning about it by observing sequence of information of data, economic data. X1 is, okay, some interest rate, x2 is something more. Economic variables, M is something that we want to predict. Okay, will the economy do well or not do well? Will the GDP be high or low, for example? And then you ask yourself, okay, when does it converge to E of M given x1, x2 through x infinity? I mean, discontinued basically. That's what there's no x infinity as such. But x1, x2, given all the information. So we'll see that this again happens very cheaply in the Martingale setting. These kind of theorems follow almost immediately. So we'll do all of this. How are we doing on time right now? Okay, so we are at 4:45. Good. Then we'll move on to Brownian motion. Now, again, have you done Brownian motion in the previous course? No. Okay, good. So we'll kind of do some things from Brownian motion in this course. All of these things, Martingales, Brownian motion, can have a full course on them. But Brownian motion is kind of, so it's a stochastic process. You know about Brownian motion as such. You might have heard about it in physics. It's trying to model how the particles move. I guess these are pollen particles that were observed by Robert Browning in water, how they were moving in a completely haphazard zigzag manner. So this was hypothesized at that time. Einstein, in one of his famous papers, proved a lot of nice properties about Brownian motion. So let me just say first of all what Brownian motion is. It's a stochastic process. Stochastic process just means collection of random variables, like indexed by time. And it's continuous for all omega, almost sure, at least on a set of probability 1. If you collect all the omegas where it's continuous, that set is probability 1. So basically it's continuous. It's a set of continuous paths, but random. So it's a building block for measuring, for modeling continuous paths. How does temperature evolve? How does pressure evolve? How do stock markets evolve? So, Brownian motion is a building block for these things. And then it has these nice properties. So this is that it is continuous. And then the increments, the change between time t3 and t4 and time t2 and t1, if they're disjoint interval, the changes in them, these are independent of each other. So how the particle moves from one time to the other is independent of how it got to that point. So that Markov property it has. So Brownian motion is independent. So now the question is, okay, so I should have, yeah. And then, okay, so the increment here, bt plus s minus bt. So first of all, increments are independent. Secondly, increments have a distribution, which is Gaussian with mean 0. So on an average, they're not changing. And variance, which is a function of the length of the interval s, independent of everything so far. Right? So increments are completely independent of the past and they are Gaussian distributed. Now, this is very useful in finance because people would like to believe, at least, and this is kind of principles that that are fairly empirically well supported, that prices change because there's new information in the market. Old information is already incorporated in the price of a stock. So it changes because of new information. So changes are independent of the past. So increments of stock prices are independent. So Brownian motion is a very kind of ideal tool in that sense to capture this stock price movement. It captures this independence due to new information. Any old information that's there, people are buying and selling, so price settles so that there's exact equilibrium with the old information. So any change happens because of new information, and so that's why this becomes a very important tool in the field of finance. So first question, when I give you these properties, is can you give me an underlying sample space omega, a sigma algebra, and a probability measure, so that on it you can define this collection of random variables with these properties, right? So now it might look like I'm trying to impress you by asking all these technical things, but this was a fundamental question which was not answered. So sort of the question is, because I'm not defined, sigma algebras and all, I don't want to stress too much on this question right now. But the point is, can I define an underlying probability space omega, a sigma algebra on this, and a probability measure, and then I'll define all these random variables bt which map omega to real line for all t, so that bt have this following property, that they're continuous almost surely, for almost all omega with probability 1. The increments are independent of each other, and each increment has a Gaussian distribution. Can I construct something like this? It was asked in assignment at CAM. Okay. Looks like you didn't get it right. Okay. Still hurts. Now we're not talking about your stitches. Okay. So the reason it's interesting is at Einstein's time in 1905, we didn't really know that such a process exists. It was just assumed by physicists. Physicists assumes all kinds of things, which look like they're true. They assume they're true. And then he proved all the properties of this process, assuming it's true. Now, maths finance people are enormously proud of this person called Louis Bachelier. How many of you have heard this name before? You can write in chat. Sushant, you should know him quite well, no? If you're still there.
Yeah.
Okay. All right. Yeah.
I mean, his thesis was the one which kickstarted things.
Yeah. So it's a beautiful, well, it's not beautiful, it's a painful story. But the story is that Louis Bachelier was Henry Poincaré's student. Poincaré is one of the great mathematicians of the early 20th century and like late 19th century. In the sense, these are polymaths who were good in all areas of mathematics. That became more and more difficult later on. So Poincaré is one of the last great ones. He didn't think much of his student Bachelier. So Bachelier had used Brownian motion to price options which exist in the France markets. Options are, these are financial instruments which say, if the stock market increases above, say, 100 pounds or euros over franc, I don't know what they had at that time in France, then you'll get some payoff. Then you can, can purchase this underlying stock price cheaper. So I guess what I'm saying is this. An option on Reliance stock can be, call option on Reliance stock can have the following flavor. It's a financial instrument that I can give to you with the property. So Reliance stock, suppose, is worth 1,000 rupees right now. And suppose this option has a strike price of 1,200 rupees. So it says after next 3 months, you have the option, not the obligation, to purchase the Reliance stock from me for 1,200 rupees strike price. Now it could be that the Reliance stock is 1,500 rupees at that time, 3 months from now. In that case, you would be happy to purchase it from me at 1,200 rupees because you're basically making 300 rupees for free. Right? On the other hand, if Reliance stock is worth 1,100 rupees, then this option is worthless to you. You're not obligated to buy something which is worth 1,100 rupees for 1,200 rupees. So these kinds of options are there in the market and they have a lot of value. They are used for risk management purposes to balance your risk, etc. So he had, in his thesis, used Brownian motion to model stock prices and price these kind of options. So this was the first paper of this sort, a lot of creativity, and he had proved a lot of nice properties of Brownian motion, fairly deep properties of Brownian motion. But nonetheless, his thesis did not get kind of first grade recognition that it probably should have. And it had also something to do with his personality. Something for all students to keep in mind, personality matters in these things, not just the quality of results. If people don't like you, it can hurt you over long term. I guess it's not just for students, for teachers also. I just never listen to it. Go ahead. Somebody want to say something? So in any case, so the point is, he didn't get much recognition. And he was kind of argumentative. So he had enormous trouble getting a good job for the next 20, 30 years. His thesis was also kind of lost. First of all, it was written in French. Okay. And so that made it somewhat difficult for the rest of the world. So he had kind of mild academic jobs, not kind of prestigious ones. At some point, he wrote a book and sent it to Paul Lévy. Now, Paul Lévy is a great French probabilist. Lévy processes, a lot of great stuff comes from Paul Lévy. And Paul Lévy looked at it and gave him a bad review. So, things were not working well for him. Later on, Paul Lévy apologized for giving a bad review to him. He said, I had not seen the book carefully enough. I had not read it enough. But, much later, by that time, the damage was done. So he had a hard life. Nonetheless, 50, 60 years later, these theses were converted into English. They were translated in English. And then I think Leonid Savage was a statistician who sent that thesis to a lot of economists worldwide that you should read this thesis. And Paul Samuelson, who was at MIT, saw this thesis and started using Brownian motion, except he used geometric Brownian motion, exponential or Brownian motion to model stock prices. Because, stock prices are non-negative and exponential of any quantity is non-negative. So then this whole thing started, and then Black and Scholes came up with the famous Black and Scholes result. We'll talk about that maybe at some point later. And the whole field of math finance kind of took off. I mean, the extremely elegant results in the world of math finance, this whole no arbitrage principle. You probably don't know about it, but maybe we'll talk about it at the right time. If you can corner Sushant, he can tell you more about these things. But the point I was trying to make was that Bachelier in 1900, 5 years before Einstein, had proved far deeper results about Brownian motion than Einstein did later. And finance people want to brag about it whenever they can to try to rub it into the physicist. So you have mentioned about R01 space. So if we consider motion of air particle with time in 0, 1, 0.
Sandeep, a question here.
Yeah. Go ahead, Aniket.
So this is probably not an answer, but so we can think of a discrete time stochastic process as a random variable on, say,
Mhm.
r to the power omega.
Yeah,
So
R to the power omega.
somehow,
Mhm.
I mean, yeah, all real sequences or something.
Yeah, so what do you want to say?
So this object BT,
Mhm.
if we equip, say, the space of all
Okay,
some
so
functions,
you're trying to construct this object.
yes,
Construct you can always do, but can you assign these properties to it? That the the independence property of the increments and stationarity of the increments and the Gaussian distribution of the increments. That's where the challenge lies.
if we were to somehow be able to define a Gaussian measure on, say, CR,
Yeah, yeah.
wouldn't
So
that?
yeah, so I'll give you some story about this. So even Bachelier had not defined it. This was defined for the first time by Wiener in 1923. He was able to actually, it's also called Wiener process. He was actually able to construct this through a series representation. So I can give you a reference or you can read up on it. But you see, it's a non-trivial way that he defines Brownian motion. It's not that straightforward. So it took the community till 1923 to come up with the first definition of Brownian motion. But Aniket, what you have in mind, or what would at least appeal to you immediately, something let me just show you in a moment. So the point was, I guess, in this, even constructing this Brownian motion rigorously was a challenge, first achieved in 1923. And now I think there are 4 different constructions of Brownian motion. But the easiest one is the one I'll refer to in a second. And let me do it right now. And that is as follows. So by the way, before that, let me answer a question that Saurabh had. So you mentioned R01. Suppose we consider, yeah, sure. So you can always define Brownian motion in multiple dimension space. It may not be Brownian motion air particle, but the noisy part of it can be driven by Brownian motion. It's like, you can have a Brownian motion with some drift, for example, or you can have a Brownian motion with a drift which depends upon where you are. So you have these stochastic integrals which are driven by Brownian motions, and those things are used a lot or diffusions to model how air particles might move. So that's commonly, that's a very common thing for physicists to model air particles or chemical reactions or many other things using Brownian motion. But basically diffusions, which are kind of, functions of Brownian motion, basically. Right. But maybe I'll talk about this more when we are doing Brownian motion. Okay, so what's Brownian motion? So your point, I guess, is there an easy way to think about Brownian motion? So Aniket, you'll probably respond to this very quickly. So suppose I look at a random walk S of n, which is sum of simple symmetric random variables xi from 1 to n independent, which take value +1 with probability half and -1 with probability half. So it's a symmetric random walk, right? Sn is just this +1, -1, n of these. And now I define at time t, B and T process, which is this symmetric walk observed at time n times t, the symmetric random walk. So you can imagine that, okay, I have observed the symmetric random walk at time nt, and I shrink the time by a factor n. So what's happening at time nt, I say is happening at time t. Right? That's why we're calling it Bn of t. So we shrunk this picture of a random walk by a factor n. And then I shrink the space, the scaling by root n. So I divide by root n. So SNT upon root n. Now, of course, I need n of t to be an integer. So I'm assuming that you can think of it as the smallest integer, the largest integer less than nt. So anyone had a comment? Why root n? So why root n? Does anybody want to take a guess? Why root n?
Because the variance is n times, so you want to keep the variance fixed.
Yeah. And any other reason? No, that's exactly right. You want to keep the variance fixed. So at time t equal to 1, you want Brownian motion, we know, is Gaussian distributed with mean 0 and variance 1. So you want the variance.
Also,
Yeah.
and also we want to assure that by CLT, like we want to
That's
apply CLT here.
That's right. That's right. So that's why Sn upon root n at time 1 looks like Brownian motion 0, 1. Like Gaussian with mean 0 and variance 1. And you can see constructed in this manner, the increments will be more or less independent. Right? If I look at sorry, Bn, did I call it above or below? Anyway, it doesn't matter. T4 minus Bn T3, this is equal to S of n of T4. I'm just using this ceiling function. N T3 divided by root n, right? Now, of course, I can divide by, I guess, root T4 minus T3 and multiply by root of T4 minus T3. And then this will converge to Gaussian 0, 1. And this time, this will converge to Gaussian with variance T4 minus T3, right? And if you look at now, Bn T2 minus Bn T1, that's equal to Sn T2 minus Sn T1 upon root n. So you can see that these are more or less independent, right? There may be some edge effects which are going to vanish as n goes to infinity. So increments are indeed independent. So I get at least the independent increments from here as n goes to infinity. So it's a random walk which I've collapsed it in both different ways. And as n goes to infinity, I get a picture which is Brownian motion in the limit. Now it has to be continuous also. I can, the way I've done it right now, I need to join points in a continuous manner. And then I have to argue that there will be a limit which is continuous. So this is what kind of motivated this whole theory of what does the limit of a stochastic process mean. So weak convergence as an area which we'll talk about in this course. Either I'll speak on it or I'll ask you to speak on it. Yeah. So that will be basically about, showing that this construction, that's how it all started, of a stochastic process. So now we're not talking about random variables converging, but whole collection of random variables converging, right? So we need a theory which justifies all of that to allow us to have these abstract random elements converge. So we'll develop the theory for that in this weak convergence. But that's how you get convergence of Brownian motion. What's nice about Brownian motion is my voice is breaking up. Is it okay with all of you? Can you hear me?
I can hear you.
Okay, so it's just breaking up on my side. So first of all, the proof of all of this was extremely interesting. Just getting all this to work, and maybe I'll ask some of you, one of you, to maybe give that proof in the class. But the Brownian motion is continuous everywhere, and it's differentiable nowhere. With probability 1, it's not differentiable on any time t. So that's the object, Brownian motion. So it's a fascinating object, all kinds of interesting properties to it. People spend a lifetime and still they discover new things about it. Once it hits a 0, it hits a 0 again, infinitely often in any arbitrarily small time interval. So those are, how often does it hit an interval once it does? So all kinds of interesting things people try to solve. It's a mathematical object which is well defined, and now you're just trying to find out its properties. But some properties are very easy. So let me ask you this property here. If you've seen this before, or if you want to just take a guess at it, let tau be the first time the Brownian motion either hits level B above or level A below. See, Brownian motion is a zero mean process. Its variance is increasing with time. So it's becoming more and more noisy with time. So conceivably, and it's a continuous process, it is going to hit level B or level A down below at some point. What's the probability that it hits B before it hits A? Does anyone know about this already? Sushant, you don't have to say. And neither should Shubhada, but anyone else, do you know about this? Saurav, have you seen this before? No. And do you want to guess? What do you think if you were living in a in a nice world, what kind of number would you expect to see? Chance of hitting? Go ahead.
Guess B over A plus B.
Oh, that's a wonderful guess. So this is for hitting B.
Hitting B first, B over A plus B.
Hitting B over before you hit A. Right?
Yeah, yeah.
What's wrong with this guess? So suppose B is
Wait.
100,000.
No, it has to be.
Can you repeat the question?
The question
I
is,
guess
what's the chance of hitting B before A?
It's
Minus A, yeah.
no, this one-
You're there. You just have to get your thoughts right. You have to put together things. So suppose B is 100 and A is
like the expect.
Yeah.
Like the expected time to first hit B or something. Or the,
So
we
should it
can-
be
Is it
A by
A?
A plus B? Something
yeah,
like that.
yeah. It's A upon A plus B, not B upon A plus B.
right.
Because
Right,
you know,
yeah.
the nearer guy you will hit first
Yeah.
than the further guy. So that's how you're broadly in the right track. So it's A upon A plus B. But you know, you have such a complicated object. Yeah, this is a stopping time. This is exactly a stopping time. But now we have to define the stochastic processes in continuous time. By the way, you know, going from discrete time to continuous time comes with a massive amount of technical problems. There are a lot of technical issues. By and large, I'm going to brush them aside inside the carpet in this course. I won't go through those technical issues. I'll give you some reading material if you want to look at them, but it takes a great deal of effort to get come. But you know, you have to conquer continuum somehow. And the way you conquer continuum is through a sequence of stopping times, which are shrinking. So you discretize everything and let it shrink down to, to get to continuum. So it's a lot of effort goes into those things. So we're going to ignore some of that, but stopping times are crucial to kind of analyze these things. But we will discuss continuous time martingales, continuous time Brownian martingales. So those are quite important. So we'll see some of them in this course. E of tau, expected time to hit level A and B, that also has a very nice answer, A times B. So very pretty things. And then you say, okay, what's the joint distribution of maximum of B, the process Brownian motion till time t, and the terminal value B of t? The maximum of the process and the final value. All of these things again have a lot of utility. In insurance, for example, you worry about insurance companies' losses crossing a threshold, because then the company will be ruined. You know, every insurance company on an average is charging you larger premium than the claims that they're paying off. And they have some buffer to protect themselves for some rare event to happen. But you could have a massive earthquake or some big event which wipes out the company. So they're worried about these ruin probabilities. It's a big area for them. So then that kind of boils down to maximum of a stochastic process crossing a threshold. So these are important random variables. They come up all the time. And you know, it's very easy for Brownian motion. You can say a lot about these random variables. So it's good to have some simple examples where you have understanding of what they look like. That gives you an idea of what other processes which are close by might look like. So, you know, just like with the exponential random variable, as we'll see, it's memoryless. So some calculations are very easy with it. And then you say, okay, for other random variables which are not exponential, do we get similar results? So one example of that sort comes up in queuing theory. How many of you are familiar with queuing theory at all?
Like in the probability course, we did some mg infinity q and also in the also some mg1 q.
Yeah, and MM1 you must have seen, right? So MM1Q has an embedded Markov chain inside it. But you know, MM1 is basically inter-arrival times are exponentially distributed, service times are exponentially distributed. And these are all memoryless processes. So the nice thing is if I just tell you the Q size, then the process is Markov. Right? You don't need to know what happened in the past to know how the process is going to evolve in the future. Is it like a branching process? No, branching process is okay. You know, a parent has many children, and then those children have many children again. Children that each parent has a random distribution. With some probability, you have no children. With some probability, you have 3 or 4 children. So this is trying to model how the population evolves, or for that matter, how the COVID virus evolves initially. That could be a branching process. And then you were wondering that, okay, will this process blow up or will this process die out? So it's very different from queuing. Queuing is more mundane, going to a bank, how much time am I going to wait in the queue? Or when I make a call on the phone, how long am I going to be on the phone? Because I'm in a queue basically. Aap Qatar mein hai. And airlines and amusement parks, all those things. So the point is you have MM1 process, and now you get, because it's a nice Markov process, you can actually get a steady state distribution of Markov process, right? You have this nice geometric distribution you must have seen. So you say to yourself, okay, this process, we had these distributions and we saw this geometric distribution, steady state distribution of the steady state distribution had this geometric tail. How general is that result? Will it be true if I didn't have exponential distributions, but like in MG1 case, I had a general distribution for service times, or GIG1 case where inter-arrival times and service times are both generally distributed? What properties will be true? So MM1 is a test case. It gives us a feel for what to expect. So same thing in Brownian motion. You get a feel for a lot of things, and then, that's a good way to, you first try to solve everything in a simple setting for Brownian motion, and then you solve it for more complicated processes. So it's a building block. So the fact that you can do many calculations exactly is very useful. And this particular result relies on a very nice reflection property of the Brownian motion. And we'll, I guess, so let me just say it very quickly here. So if I give you this Brownian motion here, and if I take any random time, any level u is crossed, and now I make a path in the opposite direction, the probability of seeing this path is same as the probability of seeing this path, because Brownian motion is symmetric on both sides. Right? So, and this is at any random time I'm stopping right now. And this will happen at random time. So even though at random time, if I reflect the process, I get two processes which have the same distribution. And that's very useful for deriving all kinds of property of Brownian motion. In particular, we'll see this distribution we can get because of that property. So in any case, so it's a lovely object, so you'll see it. And then we'll talk about weak convergence. So I have it's an ambitious agenda we have here. So we'll see how much we can cover. We might have to let go of some topics, or as I said, I may ask some of you to cover some of those topics. And that's how we cover them. So weak convergences, central limit theorem basically says that, okay, if I have, Sn is sum of IID random variables, I equal to 1 to n. If I subtract from them the mean of these guys, n times u of xi, so I normalize them to have mean 0, and I divide by square root of n times sigma. So sigma is the standard deviation, so it's sigma square is just equal to variance of xi. Then I made sure that this variable that I have here, let's call it xn, is mean 0 and variance 1 variable. And then central limit theorem says that this xn is going to converge in distribution to normal 0, 1 random variable. And what that means is probability that xn is less than or equal to small x is going to converge to the minus infinity to x e to the power minus y square by 2 dy 1 by root 2 pi. So this is what convergence in distribution means. You've seen this before, right? So this is, so you're saying a distribution function of this guy, Fn, is converging to distribution function of Gaussian random variable. So in that sense, functions are converging. But more generally, you can say that the probability measure of xn random variable, that it has a probability measure on the real line. Yeah, go ahead, Saurav. What's your question? If we consider random walk so that from time t to t plus 1, we can go to x1 to x2, where x and x2 in R, will it be Brownian? Now, random walks are not Brownian motion, right? We look at mean 0 random walk, then we shrink them in two different ways. We shrink the time and we shrink the space, and in the limit we get the Brownian motion. So how does what you're saying, how does that relate to that? Can go to x1 to x2 where x1, yeah. So right now your question is not making sense. Okay, sorry. So Saurav's question was just to me, actually, not to everybody. So I should have kept. Okay, let's carry on. Yeah. So Saurav, I think your question needs to be more precise. I think what you're saying is that suppose I have arbitrarily distributed random variables, can I still, use them and construct this process, which in the limit is the Brownian motion? And the answer is very interesting, that if your random variables have finite variance, then you can. If they have infinite variance, then you actually converge to a different process called stable processes or Levy processes. So there's this enormously elegant theory of what happens when you have this finite infinite variance random variables, and you do the same thing there. And all these are used, as I mentioned, these Levy processes, they're used to model, extreme events, for example, in the climate. So, amount of, the length, height of waves, for example, if you were to plot a distribution, you'll find that that's going to be a fat tail distribution with infinite variance. Similarly, the number of dots that one sees, or number of extreme rainfall events. So for all these Levy processes, etc., become very useful, and those are limits of these kind of more general random walks. Maybe we'll talk a little bit about this. If you're interested, I can give you some reading material, but we are going to do some extreme value theory, so we'll get to see some of this stuff. Okay, where was I going with all this? Yeah, so in central limit theorem, really what we're saying is that this xn has a probability distribution on a real line, and Gaussian distribution has a probability distribution on a real line, and these probability distributions are getting close to each other. So now you can extend this idea. You can say, okay, I know what sequence of points converging to another point looks like. Can I talk about sequence of probability measures converging to another probability measure? So that's the weak convergence theory. And it's important, as I mentioned to you earlier, is for these random walks, you get a process which has some probability distribution on the real line. And the question is, no, it actually has a probability distribution over the path of continuous C0t, probability measure on continuous paths on 0t. So it has some probability measure on that space. And now you say that through random walks I've constructed a probability measure. Is that going to converge to something in the limit? Is that going to converge to Brownian motion probability measure which has properties of Brownian motion? I'm being vague here, but we'll be, I guess, more exact when we cover this. So all of that comes up under weak convergence. But at that time, I think we'll know enough. So I'll give you all the terminology, and then we kind of show how, in particular, Brownian motion is constructed from random walks, formally, rigorously, all the I's dotted, etc., and T's crossed. Okay, so that's the agenda. And other things which I want to do in this course, and we'll see how much time we have. And like I said, maybe I'll ask some of you to read about this. This is the large deviations theory. Now, how much do you know about large deviations theory so far? Is this term that's familiar to you? Agnev, have you heard about this? Malhar?
Yeah, a little bit.
And, okay, so Agnev, your answer is also the same. So let me give you a rough idea of what we are talking about here. It's again, what I like about large deviations, what I dislike about it is that there's enormous amount of technical infrastructure that's needed to prove things in great generality. So that part, the fact that you can prove things in great generality is beautiful. Varadhan, SRS Varadhan, who's an Abel Prize winner and regarded by many, at least, when I was young, as the greatest living probabilist at that time, but certainly one of the great living probabilists. He's from India. He did his PhD at ISI in the 60s. The 60s was the time when a lot of good probability work was coming from India, from the ISIs worldwide. The whole world was looking to see what comes from there. And these were people who were doing their PhD or just completed their PhD, but very exciting work was coming out. There was this famous gang of 4. So Bahadur, Varadhan, Parthasarthi, and Ranga Rao. So these were coming up with big results at that time. So in any case, so Varadhan went to Courant Institute and developed this large deviations theory. He axiomatized it. And that's, he's done many, many great things, but this was his huge contribution. So that presents things in enormous elegance and generality. But so that part is good. But what it takes away is for a beginner, you need intuition as to what's going on. So that's kind of lost when you do all these technicalities. So there's a lot of also intuition to large deviation theory. It's very satisfying. So let me just try to explain what I'm talking about. So from law of large numbers, we know that Sn by n converges to the mean, E of x1, right? Sn is sum of IIT random variables. The average converges to the mean. Then the V convergence tells us this is the central limit theorem, right? Sn by n minus E of x1. This guy is converging to 0 by law of large numbers. If you normalize it by root n upon sigma, that's going to plus infinity. Together, you get something which is converging to something non-trivial. That's a normal 0, 1 random variable, right? Intuitively, what this means is that Sn by n roughly looks like E of x1. So, if xi is the amount you earn in each month, then your income after 24 months is roughly 24 times the expected income per month, n times E of x. And what are the small deviations around it? That's just sigma upon root n into n01. So central limit theorem tells you deviations on the, at the scale of 1 by root n distance from E of x. That smaller distance, that's captured by central limit theorem. And what's beautiful about central limit theorem is it's invariant to the underlying distribution. It just depends upon the mean and the standard deviation, the variance. All the other things are washed away. It's a Taylor series expansion. All the other things don't matter. You just need finite variance and you get this result. But large deviation talks about, now we are looking at x, which is further away from ex1, positive amount away from ex1, not 1 by root n amount away from ex1, but positive amount away from ex1. So then you say, what's the chance that Sn by n takes a large deviation, positive distance away from the mean, E of x1? Is this clear? So it's a tail event. Sn by n is going, now we are going beyond the central limit theorem regime. Central limit theorem cannot help us here anymore. It's no longer valid. All those theorems don't apply in this setting. This, intuitively speaking, we'll talk about this in a more rigorous sense, is going to have an exponential decay when the underlying random variables are light-tailed. Meaning, okay, they don't have polynomial tails, they have moment-generating functions which are finite. So they don't do crazy things. They don't take huge values with non-negligible probability. So light-tailed random variables are like exponentially distributed random variables, bounded random variables like Bernoulli random variables or Gaussian random variables. All of these guys will follow this large deviation principle. And for them, this probability will decay exponentially with n. It's e to the power minus n into some function of x. Lambda star x is some function of x. And what is this function of x? Very again, when you think about it, it's as you'd hope if you're looking for elegance. It's a convex function which is 0 at E of x. Right? Because Sn by n greater than or equal to E of x, that should roughly looks like its probability 1 by 2. It should not have an exponential decay. But once you go further away to some small x over here, then this is telling you the rate of decay, exponential decay. It's called the large deviation rate function. And it's convex, meaning if I say Sn by n is Ex plus 2 versus Sn by x n is greater than or equal to Ex plus 4, going away by 4 units should be far, far rarer than going away just by 2 units. So that's captured by the fact that this is convex. And of course, that means that it's increasing on both sides. It's non-negative. It's 0 at E of x, but it's increasing on both sides. So this is capturing the rarity of the event, Sn by n greater than or equal to x. And it's nice and convex. So a lot of nice properties of convex theory, convex programming are useful in large deviation setting. What I'm showing you here is a very kind of basic rare event. But you can imagine now, collection of lots of random variables, and you ask yourself, if they deviate from the norm, what's the chance of that happening? So large deviation theory will become useful, and it will, you'll see that often the solution to what will happen boils down to solving a convex programming problem. So very intimate connection with convex programming theory. Okay, let me just say one more thing here. So you may have heard of Sarnoff's theorem. So Sarnoff's theorem is also another thing that we'll cover in large deviation theory. We'll just keep it very basic. So suppose true distribution of random variables is mu. An empirical distribution of n sample is mu hat n. Right? You understand that, right? You generated x1 through xn. That gives you a probability distribution of the real line. It puts a point mass 1 by n at all the values x1 through xn that you've seen. That's the empirical distribution. And you ask yourself, what's the chance that the empirical distribution now, empirical distribution will begin to look like mu as n goes to infinity. But what's the chance that it actually looks like nu? So I don't know how many of you have seen this before, but this, you've done information theory or you're doing it this time? Oh, I see. So this is, of course, you'll see in information theory, but you've probably seen it already. It's basically going to decay exponentially. So for empirical distribution to look like some other distribution, it's going to be exponentially decaying e to the power minus n into Kullback-Leibler divergence between nu and mu. Right? So closer the nu is to mu, more likely the event is. Further nu is to mu, the more unlikely the event is. Right? So it's a rare event, but we can say exactly what this probability kind of looks like. So this is a part of large deviation theory, Sarnoff's theorem. Okay, and you can actually see a very nice property that, and Kullback-Leibler distance, does everybody know what that is? Or are you seeing it for the first time? Okay, so if you're seeing it for the first time, let me just show you what it is. It's called Kullback-Leibler divergence. So it's basically between two probability measures, but let me just show it between two probability distribution functions. It's going to be, so KL between density F and density F star is equal to log of fx upon f star x into f of x dx over R. Right? If this were discrete distributions, KL between two discrete distributions, P and P star, let's call them, is going to be summation log of Pi upon P star I weighted by Pi. So it's basically expected value of log of, earlier f of x upon f star of x, where under the probability measure corresponding to f. So this object you're probably going to see, far more times than you would imagine. It shows up everywhere. If you're doing a PhD in applied mathematics of some sort, computer science and system science, this is the object you'll see all the time. And one reason for that is exactly because it shows up in large deviation. It explains just chance of rare events happening. But in information theory, it's also basic event, but in some sense, it's connected to rare events even there. So it has nice properties. So now, but from your point of view, it's telling you what's the chance that something which should look like mu looks like mu. And now you say to yourself, okay, what's the chance that the mean looks like x? Remember lambda star x was our rarity index that the Sn by n looks like x. That's going to be all the distributions nu whose mean is equal to x. You look at Kullback-Leibler distance of these distributions and find the one which has the smallest Kullback-Leibler distance. That will explain, the big principle in large deviation theory is, and it's a big principle in many settings, unlikely events happen in the most likely manner. Right? So rare events have the most likely way in which they happen. So Sn by n looking like x is going to be because they have a distribution nu whose mean is x and which is closest to mu in Kullback-Leibler sense. So that's what this relationship is capturing you. Because these are all, if I give you e to the power minus n KL nu1 mu, and then I have another way of things happening, e to the power minus n KL nu2 mu. If KL nu1 mu is smaller than KL nu2 mu, then this term will be much, much larger than this term. So that's the big idea. I mean, that's the thing that you exploit in this theory, that on exponential scale, the rare events simplify. They happen in a very likely manner. And often it's a solution to a convex programming problem. Any questions or? Okay, I think I've covered lots of, let me just say very quickly what I was intending to cover, but maybe I'll talk about this next time. So I'll just spend 10 minutes maybe next time on this. But what I'm also hoping to cover in this course, one way or the other, is extreme value theory. So just like we have this elegant theory through central limit theorem of sums of random variables, there's also this theory of maximum of random variables. How does the maximum look like? So it'll turn out that, okay, typically there'll be constants dn and cn. So if you subtract cn, dn from maximum and scale by cn, you get a convergence to a nice probability distribution. So what are the distributions we converge to? So that's what extreme value theory talks about. And it's useful because, it's about maximum of random variables. So you're worried about tail events happening, some extreme event happening basically. So we'll talk about this next time. And, I'm being ambitious here, so we need not cover everything. But I'll just mention this part to you in any case, sequential learning and bandits. Let me just spend 10-15 minutes on extreme value theory and sequential learning bandits next time. So you get to see those two areas and big ideas. If you don't cover them, I may ask, if you are interested, I might ask you to take it up. So that's the plan of action. So we'll do this next time. I'll just give you 10-15 minute review of extreme value theory and sequential learning of bandits, and then we'll start with measure theory. But in some sense, it's more than a course that you're doing here. It's actually, there's more material in it than one course should have. But on the other hand, since we don't have other courses, this is one opportunity for you to see all these things. So you learn a great deal in this manner. If you were in a proper program where you do probability course 1, then you'll do stochastic process 1, stochastic process 2. You'll do a number of courses to get a hold of these material. But we don't have that luxury. So it's probably good from your point of view to see a lot of new things with certain amount of rigor. We're not going to compromise too much on rigor. So that's how I'm taking it. So yeah, so just kind of toughen up, I guess, because this will be a lot of material to study. Any questions? Ojas, was this okay for you? Did I scare you enough or?
Yeah. I think I've been sufficiently scared, Professor.
Sufficiently scared, okay. Yeah. It's you can see if you want to kind of spend that's a choice one makes. Like you want to really, that's a lot, says Saurabh. So like I said, we don't have to do all of this, and I can leave 3 or 4 topics and have some of you maybe read and present some of these. We'll see. But something close to this we have been able to manage in the past. So we'll try to see. And my guess is, and maybe Shubhadda and Sushant can say, I guess they attended one such course, although probably that was not the most intense course we taught. That was kind of somewhat on the lighter side. It's probably has been good to have seen all these things, right?
Yes, definitely.
Yeah, I mean, at this time you can't say no to this class. Come on, but maybe when you're in a more personal conversation, you can be more honest. But yeah, no, I think the feedback I got from people who've taken this course many years later, they felt that it was useful to have gone through all of this, because otherwise you don't. So in that sense, it makes sense. And we are going into a world, if you're going to do research, you really need to have a very broad toolkit. Particularly, what's nice about our program is that you get to have a toolkit with continuous tools, which is what you're learning in this course, and discrete tools, which you learn in more theoretical computer science courses. And really, you need to have both of them to compete at the very highest level. You can't just be a theoretical computer scientist working on just discrete kind of problems anymore. Yeah, so that's Saurav's point is valid. So TK, that we can always negotiate. Yeah. My job, my aim is not to make exams very hard for you. So we can cut down on some of those things. So yeah, so let's keep the jokes coming, and hopefully things will still turn out okay. All right, so I'm going to pause the